Okay, welcome everyone to the monthly meeting, first Friday of November. This evening, I'd like to welcome one of our loyal librarians, Paul, VK3 AHM, who's kindly given up his evening to come along and talk about all things batteries and amateur radio. I'll hand over to Paul, and we'll go through the session for this evening. Thank you, Paul.
Good evening on those. Tonight I was going to talk about some of the portable power batteries and that's used in amateur radio. On those, batteries have come a long way, and that's what we use when we're out and about, and that in portable power. On those, this is some of my portable setup through here. On the left-hand side there is a end-fed half wave. On those, a multi-band one, and that. And at the back here, we've got one battery that's partly assembled. So that'll show you a lithium-ion battery that I've put together. In the center there is a 49er on those. It's a kit, you know, for a little CW transceiver for 40 meters. On those, there's a 49er there, and hard to see is the actual battery that runs it on the side. So it's just a 3 18650 cells, and that in a group. And then the battery in the front there is a 48-volt battery on those. So that'd be a battery that'd be suitable for running a linear amplifier as such. We use them for e-bikes and that as well, but it's the same type of battery, 48-volt, 12 ampere hour. So that's some of the ways in that in constructing of batteries and those as such. My next slide. On those, I was going to talk about how batteries have improved over the years and the energy density on those that you would get with the different styles of battery. This chart is a pretty good comparison. You can see straight away of what the different energy densities are on some of the portable batteries that we use. Lead acid is at the bottom of the range there, 40 watt hours per kilogram. So pretty heavy battery to take portable, but okay to use for your base station to put it under the bench. On those, no problems there. They like to be topped up, you know, with a trickle charger or to be used continually on a charger because they don't like to be let go flat. As long as you remember to turn the charger off and those when you're on the radio on those because they're very noisy and those as such. Then they developed the nickel metal hydride battery on those. That was the next portable battery. We used to see it on our handheld radios on those like VHF, UHF, ICOMs and Yaesus in those around the 80s. The nickel metal hydride battery had double the energy density of lead acid on those, and it was now starting to be a real useful little portable battery. It doesn't require any battery management system. It can be just a whole lot of cells joined together, and then they're charged up with a charger. They like to be charged at the 10-hour rate or slower, so you have to use a slow charger and that on nickel metal hydrides. But otherwise, they're all quite reliable. On those, they worked quite well. And then we have the three types of lithium-ion chemistries. The first one is called LFP, which is lithium iron phosphate. The second one there, NMC, is the power tool battery. And the third one here is the laptop cell. So you can see the different energy densities on there. The laptop cell is capable of slightly higher energy density than the power tool cell. But they're the three common types of lithium-ion batteries on those as such, and giving you their energy density there. So we've now reached, 3 to 4 times the energy density that we got with nickel metal hydride. So then a much lighter than battery. On the next slide, I was going to show you some of the different lithium-ion battery types, because there's a lot of confusion with lithium-ion batteries. You'll hear one particular statement for one type of battery, and then they realize that it doesn't refer to the other type. But there are 4 main chemistries of lithium-ion batteries that we use, and that you'll see around in portable radios then as such. And an easy way to pick them up, of course, is by their common name. The first one, the lithium cobalt, it was the original battery developed by Sony in around 2000. And that chemistry is mainly used for laptops and drones. You know, in laptops, it's often a cylindrical cell, like a 18650. And then drone batteries are often lipo, you know, they're in a plastic, like in a plastic packet, and those as such. They're the cheapest type of lithium-ion battery to make on those, and they're high energy on those. They were also top of the list, you could see, you know, with the best energy density. But they had a few disadvantages in that as well with the lithium cobalt battery. They have the shortest life of all the lithium-ion batteries. Like a laptop battery may only last 3 or 5 years on those, as such. And it's also the most chemistry that's likely to catch fire, and those as such. So you might see on YouTube, you know, the videos where people drill through the side of a drone battery or something or other. Well, they'll always pick the drone battery because that's the only one that'll do that. And those, so if you puncture them on that, they can catch fire, and those as such, because they've got a lot of energy in them, and the electrolyte in them catches fire at a relatively low temperature compared to the other batteries. So that one's the highest risk. And those, but you'll see they're used in most small appliances on those. Mobile phones, and those have that type of battery in them. They're the most common on those of the small appliance batteries. You wouldn't use them in a large appliance because of the fire risk of that with them, only in small appliances. And then Panasonic developed an improvement on the laptop cell. They added aluminium to the chemistry, and the common name for that is the Panasonic NCA battery, which is nickel cobalt aluminium. Oh, the NCA stands for. So Panasonic is the only company that manufactures that particular chemistry. They developed it themselves, and it's another high energy chemistry on those, but it can only be made in small cylindrical cells, much like the lithium cobalt. They tend to, it's a high power laptop battery, and that and such. And then that particular battery from Panasonic, Tesla made a deal with Panasonic to use that particular cell right from the very first, when they started off making the Tesla Roadster on those. So all the American-made Teslas on those that use that particular battery. And Panasonic runs the Gigafactory in the US on those and manufactures batteries there for Tesla and those as such. So that was the lithium, the Panasonic NCA battery. The most interesting battery, and the one that they've developed now, is this one there called the NMC on those. It was developed by Professor Goodenough, I think his name was, and he was from Canada, from one of the universities. And he developed that particular chemistry, and we call it, it's the power tool battery. This particular third battery was the one that developed the lithium-ion power tool industry, because it was a safe battery, high power, you know, it can deliver 10, 20, 15 amps per cell, no problems at all, and a much more useful battery in that way. Also had a long life, and that as well, longer life than the other two earlier chemistries as such. So that's why if you have your power tool battery, you know, and it'll last 5-10 years easily on those with a power tool battery, even if you're using it a lot, you know, 2,000, 3,000 cycles, it can handle on that no problem. And that was the particular battery that started the electric car revolution. So all the electric cars on those use the NMC battery and those as such. So Nissan, Mitsubishi, Renault, Volkswagen, all of them were making electric cars, and they used that particular battery and those as such. So the last battery we were talking about was called lithium iron phosphate on those. It was originally developed as a storage battery on those by the Chinese, 2007, 2008. It's been around for quite some time on those. And the lithium iron phosphate battery is one of the safest chemistries. It won't catch fire. You know, you can drill through the side of it, like what they do with the YouTube videos, and it won't catch fire, won't even smoke on those. It's perfectly safe in that design battery. So it's probably the most common one that's used in amateur radio on those, you know, because it works, the particular voltage suits 12 volt. So 4 cells in a lithium iron phosphate battery is perfect as a 12 volt battery. So they're often used for mobile and portable use and that an amateur radio. And what's happened actually is the electric cars have now changed over to the lithium iron phosphate battery on those. So 60–70% of the cars that are in sale in Australia on those use lithium iron phosphate batteries now. Tesla is not using the Panasonic chemistry anymore on those, the Model 3 and the Model Y that they're selling in Australia all use the new lithium iron phosphate battery. Yeah, so when dealing with lithium ion batteries, because of the four main chemistry types on those, the characteristics of all four and that are quite different. And those, so you know, the fire that you see where someone's drilled through the battery, or they bought a cheap scooter or something or other, it's probably got a lithium cobalt battery in it. They've just been using a drone or a laptop cell, you know, a cheap source of batteries on those for the particular device. So I've been making batteries and involved with batteries probably since 2007. I brought a battery along with me and I'll pass it around just to show you some of the methods of construction on those. So this one is a 11 volt lithium ion battery. It has a battery management board on it. It's made using the NMC type cells on those, so the same type of cells as used in power tools and that, and with a battery management board on top on those, the battery management board, it monitors the voltage of each blocks, and when a block of cells reaches 4.2 volts, it shuts the charging off. So the microprocessor on the board, you know, monitors all the cells. So it shuts the charging off at 4.2 volts, so the battery can't be overcharged. And then also when it's discharging, it'll shut the battery down when the cell block reaches 3.2 volts, so you can't over discharge it. So all those functions on those are actually monitored by the battery management board. So on the board there itself, the MOSFETs through here on those turn the battery on and off, and they've got 5 there in parallel on those, so that it's a very low resistance. The actual you know, resistance of the board is 2 or 3 milliohms, and those as such. The top part of the circuit board there is the balance function. So every time that the battery is charged, it monitors the voltage of each cells, and it just bleeds off the highest particular block. So in other words, if you've got 3 blocks of batteries there, one might come to 4.2 volts, the other one might be 4.15 on those. So the higher block, the battery management board bleeds off that voltage down to the lower one. So in other words, it rebalances the battery every time that it's charged. And that's just some of the maintenance on those, on the lithium-ion battery. And it's done by the circuit board. This particular one here has a rating on it called 3S, 60 amps. So it's designed for three groups of cells in series. And 60 amps is the maximum continuous output on those from the battery management board. So a small board like that can, that particular battery has an output of 40, 50 amps. On those, it'll easily run a 100-watt radio on those as such from a small battery. But that particular battery is only 9 ampere hour. So you might be talking for a couple of hours on that on your radio, and that before it'll go flat, and those as such. So they're made in smaller and larger sizes as such. The cells are glued together, and then a welder, what we call a tab welder, is used for welding the cells onto the connectors. The particular metal strip that's used is pure nickel. It's a nickel type strip. You can also get a nickel plated steel, but corrosion starts to get into the actual joints on those after a while. And the nickel plated steel ones, which you'll see in some of the cheaper constructions, you know, after several years, corrosion can cause the tabs to lift. But the pure nickel, if you use pure nickel on those, it has a much longer life. Yeah, so those are some of the things that we look for in that when we're constructing a battery. These particular batteries are 3.7 volts per cell. That's their nominal voltage. You know, they're 3.2 when they're flat, and they're 4.2 when they're fully charged. But their nominal voltage is 3.7 volts a cell. So these particular batteries don't match a 12-volt battery. 3S comes up at around 11.4 volts, and 4S comes up at about 15 volts, 14.5, 15 volts. So they're not very good at doing that on those. It doesn't really match a 12 volt. It does match 24 volt quite well, but 12 volt not so much. Well, I'm open to questions now on those. So I've pretty much covered what I wanted to cover on through there. So we'll start off with some questions. On those, 5 of the MOSFETs on those operate on the discharge function and 5 on the charge. So it also switches the charger in and out. So once the battery is fully charged, one of the blocks has reached 4.2 volts, the board will disconnect the charger, and the charger usually goes to green at that stage. The boards, I buy them through AliExpress on those, so they're all manufactured in China and those. So yeah, AliExpress is probably the best place to purchase them from in those. So you can buy quantity or in single values, small values. eBay, you'll also see them on eBay quite a bit as well. Yes, it is. Yes, you do. You have to buy the correct board for the configuration that you want. You could have a 2S board, which has 2 blocks of cells in series, or you could have 3S, 4S. They go right up to 20S on those, which may be a 96-volt battery. So boards are available, you know, for all those different configurations. And when you buy a battery management board, it'll also have its maximum current that is designed for as well. On those will be a specification and that with the board. Okay, the question was, do the boards change between constant voltage and constant current? No, the boards don't. They only switch on and off. So if you want constant current charging up to a certain voltage, you have to use the correct charger on those. So lithium-ion chargers are designed that way. They're a constant current charger, which then charges up to their maximum voltage. You can use a charger which is slightly higher in voltage than the rating of the battery because the board will switch it off when it's fully charged. But the current of the charging is set by the charger. So you can't charge them from say a ham radio power supply. On those, you have to use a constant current power supply or a lithium charger. Okay, so the question was about a battery mower that had a battery that was dead flat and it wouldn't charge up on those. So what would we do in that situation? The battery management boards are designed so that you can't charge the battery if the voltage has dropped below 3 volts. That's a safety consideration because when a lithium-ion battery is allowed to go below 3 volts, a chemical reaction starts to occur inside the battery and the battery develops a high leakage. It may not happen straight away if the battery is left flat for a couple of months and this chemical reaction starts to occur within the battery. So they designed the lithium-ion chargers not to charge a dead flat battery and those as such. You'll see on YouTube where they kickstart them, you know, by putting a wire across to a good battery on those and kickstart a battery that's flat. That may work if the battery hasn't been flat for long. But if the battery has been flat for some time and the chemical reaction has occurred inside the battery will start to overheat while you're charging it because it's developed a high self-discharge rate. So it can be unsafe on those and that to do that, to try and discharge a battery that's been left flat for some time with lithium ion on those. And the best way to tell is if the battery is starting to heat up on those as you're charging it, you've definitely got a battery that's unsafe to charge. Lithium-ion batteries do not heat up while they're charging, so that's indicating a fault situation. So trying to kickstart a lithium-ion battery or charge it when it's been left flat on those is not a safe practice. Good, yes. Often they will come off zero on those if they haven't been left flat for too long. So this is an interesting question on those. The question was, does the NMC battery on that contain cobalt? And the answer is yes, it does on those. So this is the original power tool battery. It contains nickel, lithium, of course, nickel, magnesium, and cobalt. Nickel is becoming quite expensive on those. The price of nickel has risen huge due to demand for lithium-ion batteries. And cobalt also is only mined in one place in the Congo on those. And there's a lot of ethical issues regarding the mining of cobalt. So both of those metals, nickel and cobalt, on those we would prefer not to see or not to be used within lithium-ion batteries. This is one of the reasons why the lithium-ion phosphate battery has taken off on those as such, because it has no cobalt and no nickel in it on those, and it's quite a safe battery on those, and which will not catch fire. So therefore, the lithium-ion phosphate battery has become more commonly used. It was originally developed as a storage battery for large energy storage on those. So it's the type of battery that should be used for any large energy storage purpose or in a large battery pack, such as an electric vehicle. So question, does the battery management board take any current? Yes, it does. The battery management board does take a small amount of current out of the battery while it's detecting the voltage of each cell. So for that particular reason, you should recharge a lithium-ion battery every 3 months on those. So that's part of the general consensus in the industry that if you have a lithium-ion battery, you should recharge it every 3 months, because the battery management board will take a small amount of power while it's monitoring the cells out of the battery. For instance, if you have an electric bike, you put it in your garage, you come back 12 months later and you decide you want to ride it, and you go to charge it up and you find it won't charge on those because the battery has been allowed to go flat and left flat for too long. So it can be 6 months, it can be 3 months, but generally we recommend recharging a lithium-ion battery every 3 months. The question was about lithium-ion phosphate batteries on those, and whether they can be discharged from flat, and whether a charger can kickstart them on those as such, and that they have a greater resilience, I think it was. The lithium-ion phosphate battery has the longest life. It's 15 to 20 years. So some of these earlier batteries, as I said, like the laptop cell, maybe 5 years, and those as such. But lithium-ion phosphate is 15 to 20 years. And so they will last longer in the appliance, such as an electric vehicle. You're looking at now battery lives of 15 to 20 years in purchasing an electric vehicle. So the battery will probably last the life of the car. The other thing, they don't mind being discharged to being flat. Like you can charge them to 100% and you can leave them at 100% without any degradation of the battery with lithium-ion phosphate. So they don't really have any issues at all there. They can be left flat. They can be 100% discharged each time. They're quite rugged in that way, and they have the longest life of the lithium-ion chemistries. The question is, with the storage, is there a storage voltage for charging these batteries? Like, what should you do with a lithium-ion battery if you're going to put it in storage and those as such? The first battery, the lithium cobalt one on those, it's best to store it at 70% charge on those as such, rather than storing it at full charge, because it will degrade. Its calendar life is about 5 years, and it will degrade if you leave it fully charged all the time. You'll shorten its calendar life, is what I'm saying. But the other chemistries, NMC, which is the power tool battery, and lithium-ion phosphate, they recommend that you charge them to 100% if you're putting them in storage on those, and then top them up every 3 to 6 months. And so they don't have any problems on those with degradation being stored at 100% of charge. the question was, what are the reliable sources and that for purchasing these batteries as such? One reliable source I know, the lithium iron phosphate battery, who's a company that's been selling them over 10 years, is a company called EVWorks in Western Australia, in Perth. So they import lithium iron phosphate batteries that people use in car conversions. So I've been involved in electric vehicle conversions, right from 2007. And this was the main company that we would purchase our batteries from. The lithium iron phosphate battery is only manufactured in China. So there aren't any sources, US or Korean sources. Well, actually, Samsung does also manufacture some lithium iron phosphate. But the larger ones, the larger prismatic lithium iron phosphate, are only manufactured in China. So yes, it's a matter of finding a good source for the batteries as such. So that's one source I know of. Yeah, so what was the difference between prismatic and the other types of cells? I suppose lithium ion cells come in three main constructions. The most common one is the cylindrical cell, which was used for laptop cells and such, and is also used for power tool cells. So a cylindrical construction is the cheapest to manufacture, and it's wound in a spiral. So it's just wound in a spiral inside the battery and then placed inside a metal can. The other type of cheap construction is the drone battery, where the battery is made out of plates with a separator between them and then put inside a plastic package, like a plastic pouch on those. So that was another, it's a lightweight construction on those, but it doesn't have any, there's no mechanical strength. It must be put into somewhere where it's not going to be compressed, and that as such. So that's the pouch cell. Now the prismatic cell is a large battery, larger than the cylindrical cells. They have flat plates in them, and they're quite often in a plastic or aluminium case. So electric vehicle cells are usually prismatic, and those are such, and so is energy storage on those. So it's just a larger footprint of lithium-ion battery, and they're such, and we call them prismatic cells because they're rectangular. They're shaped like a prism. Any other questions there as such? Okay, thank you very much.
Congratulating Paul on a very entertaining session. So thank you for taking the time. It's a very interesting topic, and one that's only going to continue to grow with interest for everyone, I think.